So normally we would do this in class together, this little problem that we're going to talk about here, but I'll just do it for you. So you're welcome. We're basically going to skip the whole front page of the 6.3 notes because it's just vocab type of stuff. So I'm just going to explain in words what's going on and then we won't have to worry about it. Okay. So what I'm going to do is I'm going to give you a visual of what's happening in 6.3. It's just an extra thing that we can do with our standard normal distribution. So what I'm going to do is I'm going to say that there were 4 scores on a quiz, or just, it's probably easier to think of, I have the numbers 2, 4, 6, and 8 in a hat. I'm going to take one out, write it down, put it back, take another one out, write it down. So I'm going to make ordered pairs, but with replacement. So what I need to do is I need to come up with all possible ordered pairs. Okay, there's 16 of them, so it wasn't too bad. Again, usually I make you do this on your own, but oh well. So here is all possible ordered pairs that we could come up with. Notice the order matters. So like 2, 6 is different from 6, 2, things like that. All right. And then we're also going to calculate their means. All right, so obviously 2 plus 2 is 4 divided by 2 gives you 2. 2 plus 6 is 8 divided by 2 gives you 4, so on and so forth. So here's the ordered pairs. Here's the mean of the ordered pairs. All right, what we're going to do then is we're going to draw a histogram of these. And I just have to tell you that earlier today, the doctor pulled up a really cool histogram when he was checking on something for Briar. So I was super excited to see a histogram being used in real life. So it was pretty awesome. I was excited. Anyway, I know you weren't. So here's what I did. I made a frequency distribution. Remember we did those back in chapter 3 on the computer, and I made a histogram. Here's what I want you to notice. This is a symmetric histogram. All right, so what I did is I took just 4 numbers that are all different. So if I made a histogram out of these, it would look like a rectangle. Okay, each box would just be a frequency of 1, so on and so forth. So I took 4 numbers, figured out all the possible ordered pairs, calculated their means, and their means now have a symmetric histogram. Now, it's not quite a normal distribution because, again, if I try to draw the curve, there would be lots of empty space. But here's what the central limit theorem, which is what 6.3 is called, here's what it says. I gave you pretty much the most basic one we could do. If I made you come up with ordered triples, okay, there would be, let's see, 4 times 4 times 4 is 64. There would be 64 different options rather than just 16 different options. So what you would have is you would have even more different means, and your histogram would get more and more to be a normal distribution. Or if I had you come up with all possible 4 numbers in a row, all right, then you would have even more. And again, that's a really, really small sample if you think of that. 4 numbers, we're choosing 2 of them. You have to think of what we're doing as we have like 100 options and we're choosing to come up with ordered 30s or something like that instead of just ordered pairs. Okay, so the more you do that, the bigger your sample size, the more and more this right here, this distribution is going to become normal. So this is what the central limit theorem is all about, is you can take any data set you want. Okay, we took 4 numbers is all. You can get their ordered triples, ordered doubles, ordered whatever. Okay, we're going to have to do more than that. But when you calculate their means, right, their means become normal. So not the numbers themselves, not the actual data values, but when you take ordered, again, ordered 30s or whatever it is, you're doing random sampling with replacement. That's what we're calling it, putting all the values in a hat and pulling them out. Okay, then when you have their means, then it will make a normal distribution. So even though you don't really have to know or remember that, it's just what makes section 6.3 work, is you can take non-normal data and do means instead, and then you can use your normal distribution. Okay, so again, I know that probably doesn't make any sense at all, but we'll just go with the problems and hope that it makes sense. So again, we're going to ignore the entire front page of 6.3. The only thing that's important is now we're going to have a new z-score. Okay, so here's the z-score you're going to use instead. X bar minus mu, okay, over sigma over the square root of n. So instead of asking you for a certain data value, it's going to ask you for the mean of some people or whatever it is. Okay, and then the n is your sample size. So people usually freak out. How do I know when to use which one? All right, and I will answer that when we get to the last problem. Okay, so this is the one for today, or for 6.3. 6.2 looked like this. Okay, so there's your two different z-scores that you will have on your formula sheet whenever we get to the chapter 6 and 7 test. So again, most people kind of worry, how do I know when to use which one? All right, so here's how you're going to know the difference. So this problem says A.C. Nielsen reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume the variable is normally distributed and the standard deviation is 3 hours. If 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean number of hours. So here's how you know to use 6.3. It's asking 20 children, and all the rest of them, it didn't give us a sample size. 20 children, we want to know the probability that their mean is something special. Okay, in this problem, it's going to be greater than 26.3. So most people say, how do I know which number goes where? X bar is just like the X. It's the number they're asking you to check on, which is the 26.3. So we're going to have Z equals 26.3 minus the average they give us is 25 over your standard deviation is 3 over the square root of 20. Okay. So again, you can do this all in your calculator at one time. You just need to make sure you have parentheses there and parentheses there. Okay, parentheses around the whole top and the whole bottom. And when you do that, you should get 1.94. So remember, you're always going to round your z-score to 2 decimal places. You should get 1.94. After that, it's exactly what we did in 6.1 and in 6.2. So you're going to have 1.94. We want to know above that. Okay, we want to know above 1.94. So again, you have two options. The shortcut is to look up negative 1.94. That will give you your answer right away. Otherwise, if you look up positive 1.94, remember it gives you that amount, that would give you 9738. So we need to do 1 minus 0.9738, which gives us 2.62%. Now, usually I stop here and say, does that really make sense that it's that small of a percentage? The average was 25. We're checking on 26.3. The standard deviation is 3, so it's not even half of a standard deviation away. Why is our z-score 1.94? Mathematically, the reason is because we're making this denominator different. It's not just 3 anymore. It's 3 divided by the square root of 20, so it's an even smaller number. Okay, so here's the reason. We're not just asking one person. We're asking the mean of 20 people. All right, so if you think of if you're asking 20 people, 20 children, how long they watch television, you're finding the mean of those 20. You're asking that to compare that to 26.3. When you take the mean of a group of people, it scrunches it in. Okay, remember, it will kind of get rid of those outliers and everything like that. So yeah, we probably have some kids that watch way less. Sometimes we probably have kids that watch way more. But overall, the average, the mean, is going to be kind of close to 26.3. That's why this percent is so low. Okay, or sorry, the average is going to be closer to 25, which is why the 2.62 is so different. So this one's really hard to think about. Does it make sense? 6.2, you should be able to ask yourself, does this make sense? And should be able to answer it pretty easy. This one's a little bit trickier to do that. All right. So next one, the average age of a vehicle registered in the United States is 8 years or 96 months. Assume the standard deviation is 16 months. If a random sample of 36 vehicles is selected, find the probability that the mean of their ages is between 90 and 100. So again, now we have two different z-scores. So we have to do z equals 90 minus 96 over 16 over the square root of 36. Hopefully we all know that square root of 36 is just 6, but I'll write it in there just in case. So again, you're going to type that into your calculator, negative 2.25. Then we have to do that again with 100. 100 minus 96, 16 over the square root of 36, and you get 1.5. So notice how far away our z-scores are. Okay, even though we're only 6 data values away, 6 values is all, our z-score is negative 2.25. That's a really quote-unquote big, even though it's negative z-score. All right, again, we're only 4 away, but it's still 1.5. So these are going to be a lot more dramatic. So when I draw this one out, we have negative 2.25 and positive 1.5. Looking for in between. So again, you just need to look up both of them. Negative 2, there's no shortcut to these. 0, 1, 2, 2. And then 1.5 gives you 9,332. So 9,332 minus 0,122 is going to give you 92.1%. Right, so again, no shortcut to that one. And again, this is a really high percentage because your z-scores are so big. And again, that's because we're finding the mean of 36 different vehicles. So it's would be a lot less likely to find one car between 90 and 100, but the fact that we're finding the average or the mean of 36 cars, it's going to make it a lot more likely. All right, here's one that will compare the two. So this is where you're going to have to ask yourself, do I use 6.2 z-score or do I use 6.3 z-score? And I'm going to give you a little hint. So the average number of pounds of meat that a person consumes per year is 218.4. Assume the standard deviation is 2.5, distribution is approximately normal. Find the probability that a person selected consumes less than 224. Part B, it says if a sample of 40 individuals, find the probability that the mean of their sample is less than 224. So using the same number, but part A is asking about one person, part B is asking about the mean of 40 people. So this is a 6.2 problem, this is a 6.3 problem. Again, are you going to remember that when it's not labeled in your chapter 6 and 7 test? Maybe not. So here's my hint. You can always use this one. Even though it doesn't use a mean for part A, that doesn't really matter. X and X bar, doesn't matter which one it is. The reason is this. The sample size for part A is 1. Square root of 1 is 1. When you divide by 1, it doesn't change anything. So if you're ever unsure, pick this one because your sample size will be 1 and it won't hurt you. Okay? So I'll do it the way you're supposed to do it, but again, it won't hurt you if you always use the one we just learned right now. Okay, so z equals 224 minus 218.4 over 25, and that gives you 0.22. 0.22, and we want less than. We always like the less than problems because that's exactly what the chart looks like. So you're going to look that up and that will give you your answer right away, 5871. So 58.71% is your final answer. Okay, now again we're going to look at the mean of 40 individuals. So now we're going to do 224 minus 218.4 over 25 over the square root of 40. That's going to change it to 1.42. So notice how much bigger that z-score is compared to the one up above. Okay, again, it's because it's way more likely that the mean of 40 is going to be below 224. So 1.42 below that. Again, look that right up, 92.22. 92.22% is your final answer. Okay, so really the only difference here, again, is you, instead of just doing your normal z-score, you have to divide it by the square root of your sample size. And what you're looking for is you're looking for a sample size and the word mean in your problems.